Assalamualaikum. In previous lectures, we have discussed a lot about the conventional network architectures. We have talked how these switches and routers work. We also talked about the fundamental principles of routing and switching. Now, the in the last 2 decades, there has been a lot of developments in the networking architecture side, especially due to the different requirements. Software-defined networks have been introduced. Software-defined networks are flexible and they provide several capabilities and several advantages. Yeah, so in this session, we will talk about the software-defined networks, their architecture, their key components, and the key characteristics that differs from the conventional or the traditional network architectures. We should also look at the historical evolution, how software-defined networks have evolved during the last decade. So let's begin with the session.
Before starting our discussion, let's discuss the different reference books or reference materials. Basically, in this session, we aim to understand the transition from conventional networks to conventional network architectures to software-defined networking. Our discussion is based on two primary sources. The first source is a book titled Foundation of Modern Networking, SDN, NFV, QoE, IoT, and Cloud by William Stallings. This book was published by Pearson Education in 2016. The second source is collection of specifications and resources provided by the Open Networking Foundation available on their website. These resources provide both theoretical insight and practical relevance as we explore this significant shift in the world of networking. The core objective is this session is to develop a solid understanding of why there is a growing shift from traditional networking models to software-defined architecture. And in this session, we will cover some key topics such as the motivation for SDN, foundational concepts and definitions, the main components of SDN, and the evolution of SDN architectures. Let's begin by examining the motivation behind the development of software-defined network. The traditional network architectures rely on distributed control logic embedded within the individual network devices such as routers, switches, firewalls, and the load balancer. Each device makes its own independent decisions regarding traffic forwarding and policy enforcement. For example, if we look at the figure given in the slide, consider a traditional IP network consisting of two layer 2 switches S1 and S2 and four routers R1, R2, R3 and R4. In this setup, each switch is responsible for its own switching decisions or the routing decisions, while each router independently determines its routing behavior. All policy configurations such as routing protocols, access control lists, and quality of service rules are specific to each device. This kind of architecture is known as distributed control plane architecture, where both the control plane, which is responsible for decision making and configurations, and the data plane, which is responsible for forwarding packets, are present in every device. The control plane is typically configured by the network administrators through a command line interface. While this model is quite manageable in small networks, it creates a significant challenge as the network grows in size and its complexity. There are four main issues with the traditional network architecture that we have shown in the slide. These issues are static and rigid configurations, vendor lock-ins, lack of global network view, and slow innovation and experimentation. One of the major issues is the static and rigid configuration of devices, because each device must be configured manually, making changes across the network, such as updating access control lists on hundreds or thousands of routers. It is time consuming and error prone. For instance, if policy change needs to be implemented, it has to be manually pushed to each relevant device. This manual process not only slow down the operations but also increases the risk of misconfigurations. In dynamic environments where traffic patterns and user demands change frequently, traditional networks are too slow to adapt to them. Another critical limitation is vendor lock-in. Vendor lock-in means once an organization procures networking hardware from a specific vendor such as Cisco or Juniper, they often become dependent on that vendor's proprietary systems, APIs, and their interfaces. Integrating equipment from another vendor becomes problematic due to the incompatible operating systems and closed protocols as compared to the other vendors. While open standards exist, Vendors often implement them differently, making interoperability difficult without additional customization and support from the vendors. As a result, organizations are often forced to stick with their original vendor for extension or upgrades, which can be costly and restrictive. Another issue is the lack of global network view. That is a key challenge in traditional architectures. Since each device operates independently, there is no centralized visibility to overall network state. Each router or switch only has knowledge of its immediate connections, leading to locally optimal decisions that may not be optimal from end-to-end network perspectives. For example, in the case of a link failure somewhere in the network, not all devices are immediately aware of the issue. They must rely on mechanisms like hello packets or spanning tree recalculations to detect the change, which introduces a delay in and inefficiency. Troubleshooting becomes particularly very difficult as no single entity has a full view of the network topology or its current status. The fourth issue is the traditional networks hinder innovation and research. As most of the networking hardware relies on proprietary firmware and closed APIs, it is nearly impossible for researchers or third-party developers to deploy new protocols or services without full cooperation from hardware vendors. Even for example, if a university team designs a promising new load balancing algorithm or routing protocol, testing it on actual devices typically requires vendor approval, specialized knowledge, and sometimes contractual agreements for the conventional networking architecture. This restricts the rapid experimentation and significantly slows down the technological advancements in the networking. So these are these four major issues. In addition to these four major issues like the static configurations, vendor lock-in, lack of global visibility, and limited support for innovation, these issues are compounded by additional operational problems. Manual configurations are prone to error and inefficient, especially in large-scale networks such as the network operators and the large enterprise organizations. Updating security policies like ACLs across thousands of devices is a daunting task. The distributed control plane lacks the coordination, which delays responses to the failures and makes real-time network management nearly impossible. So after discussing the limitations with the traditional networks, let's talk about the modern requirements that are emerging from the developments in different fields. Basically, the traditional architectures are not programmable. They allow configurations but not dynamic behavior adjustment. For example, during a peak traffic conditions, the traditional devices cannot automatically adjust routing paths or enforce load balancing based on real-time analytics. Modern network environments such as cloud computing, virtualization, and multi-tenant services introduces new requirements that traditional networks simply cannot meet. These applications require programmable, flexible, and adaptive control mechanisms. They often demand real-time provisioning and adjustments of the resources. For instance, a data center might need to analyze incoming traffic and adjust switch behavior immediately. This type of responsiveness is not possible in traditional networks that rely solely on static CLI-based configurations. Furthermore, the traffic engineering and security policies increasingly require dynamic, context-aware behavior. Without programmability, enforcing security policies based on traffic type, source, and context becomes impossible. Traditional networks are not designed to adapt to these dynamic demands, making them unsuitable for modern service delivery models. Another requirement, an essential requirement in modern network architecture, is also centralized control and global network view. Over the past decade, rapid advancements in various technology domains have increased demands on telecommunications and data networks. These developments necessitate centralized control and management of networking policies, along with the complete visibility to network operations. Centralized decision-making enables network-wide optimization, such as the shortest path routing and congestion avoidance. And it also simplifies troubleshooting and monitoring. In the accompanying slide, in the figure shown in this slide, it is illustrated that both centralized and decentralized decision-making The green circle represents a centralized controller that makes all network decisions, while the red circles depict network nodes that execute these decisions. In a centralized architecture, a single controller governs the entire network, whereas in a decentralized setup, each node operates independently and makes its own decision. Another requirement of the modern services architecture is the automation and orchestration. Basically, the modern networks must support the automation and orchestration of various workflows. Network provisioning and management should be automated through application programming interfaces, which reduces operation complexity and minimize human error. These capabilities must align with the contemporary software engineering practices such as agile methodologies and DevOps principles. Automation involves decision making based on single input, typically using if-else logic. In contrast, orchestration involves managing multiple inputs, setting priorities, and defining sequence of the actions, often attaching weights or significance to each of the decision. Traditional networking architectures lack native support for such dynamic automation and orchestration. Moreover, the integration of artificial intelligence and machine learning further enhances automation and orchestration. Networks should be capable of adapting dynamically based on AI and ML models that analyze historical data to inform real-time decisions. This intelligent orchestration ensures optimal network performance and improved service delivery. There is yet another requirement for the innovation and experimentation. Traditional networks often lack the flexibility required for innovation and experimentation. However, modern technologies and services demand the ability to rapidly prototype and test new ideas without requiring changes to the hardware. This calls for software-defined solutions that allow researchers and operators to implement new protocols and ideas directly in software. For instance, Google's B4WAN uses software-defined network to optimize inter-data center traffic, achieving high utilization and rapid failure. Without SDN, such dynamic management would be impossible due to the limitations of proprietary protocols and static configurations in legacy devices. Innovation and experimentation typically follow cycle: idea generation, data collection, testing, and iterative improvement, enabled by the programmable software driven network environments. There is another requirement from the modern services architecture, that is the seamless integration with the virtualization and cloud platform. With the growth of cloud computing and virtualization, network must support seamless integration with virtualized networks environments. This includes enabling network virtualization, where logical networks operate independently over a shared physical infrastructure. Technologies like network function virtualization and containerization of network functions play a key role in this transformation. As shown in the diagram shown on this slide, a single physical network can be partitioned into multiple logical networks, each governed by distinct policies for routing, security, and quality of service. Traditional architectures are poorly suited to this model, as they require static configurations and lack the flexibility to support dynamic policy-driven control. Many services demand that each virtual network have its own control and decision-making capabilities, including traffic management, security enforcement, resource allocation, independent of other virtual networks. Yet another, there is a need for improved security and policy enforcement. Modern networks must provide enhanced intelligent security and policy enforcement techniques. This requires a fine-grained policies and dynamic enforcement mechanisms, which are challenging to implement with a distributed control plane. Instead, centralized control enables real-time threat detection and rapid response, along with the improved segmentation, isolation, and access control. Traditional architectures lack the agility and intelligence required for these capabilities. To meet modern demands, network must evolve to support centralized, policy-aware, and responsive security architectures. So these were the few requirements. These were the basically the limitations of the traditional networks and some new requirements from the emerging services the architectures.
So if we summarize the motivation for software software-defined networking architectures, we have seen that there are several limitations in the traditional network architectures. For example, they do not allow the automatic configurations, the automation or orchestration is not possible. And furthermore, there are some emerging requirements due to the cloud computing and software-based services that have been introduced in the recent decades. We have also seen that in the emerging networks like the 6G, 5G networks, there is a lot of requirements for the control, flexibility, and scalability requirements. For this purpose, SDN can provide flexible and controllable and centralized network architecture, which is not flexible. It allows the configurations and network management to be automated, and a lot of things which are redundant in the traditional networks that have been removed. For example, furthermore, the innovation with software-defined networks can be quite expedited because there are the new protocols and new applications can be developed with the different APIs which are available.
We have discussed the limitations of traditional networks and evolving requirements of modern services. SDN presents a compelling alternative to traditional networks architecture. SDN is a network architecture that decouples the control plane, which makes routing decisions, from the data plane, which forwards traffic based on those decisions. Formally, SDN enables the control plane to be directly programmable while abstracting the underlying infrastructure for applications and services. This definition directly aligns with the modern networking needs we previously discussed. SDN is specially designed to address the limitations of traditional networks, supporting flexibility, automation, and innovation. To understand SDN better, it is important to review the traditional router or switch architecture. In such systems, the control plane and data plane coexist with each device. The control plane, often vendor specific, for example Cisco or Juniper, runs the routing protocols and maintains the routing information base and implements policies, network management, and access control as shown in the slide. The data plane handles packets forwarding using the forwarding information base, performs ingress and egress processing, applies access control lists, and handles encapsulation, supports network address translation, and QoS at line rates, for example 1 gigabit per second or 10 gigabit per second or more. For example, in OSPF, which is the Open Shortest Path First routing protocol, the control plane exchanges link state information and computes the shortest path using Dijkstra algorithm. These routes are stored in RIB and then installed in the FIB. RIB is the routing information base and FIB is the forwarding information base. The data plane then uses the FIB to forward packets. In traditional networks, each device independently runs these functions, leading to complex distributed control mechanisms. On the other hand, when a packet arrives at an ingress interface on the data plane, the forwarding engine checks the forwarding information base for the destination IP, and if the matching entry is found, then packet is either filtered or marked for QoS, or network address translation is applied. And finally, the packet is sent to correct egress interface. All this happens at very quick rate. The core idea of SDN is to separate the control plane and data plane. In SDN, all data plane functions remain on individual network devices, but the control plane is centralized into a single logical controller. This centralized controller communicates with all networking devices to provide control decisions. Architecture allows for simplified network management, efficient resource allocation, and improved scalability. While centralization may seem to increase computational requirements, it actually reduces the redundant processing across multiple devices. Instead of each device performing its own computations, a centralized controller can optimize the network holistically. As shown in the figure, the control plane has been centralized into one node, and the other nodes like node 1, node 2, node 3, they all implement the data plane separately. The decisions are made in the control plane and they are then exchanged to the node 1, node 2, node. After understanding the differences between traditional networking and software networking, software defined networking, let's explore the simplified architecture of SDN. SDN is typically structured into three layers and interacts through three main types of API. First one is the application layer, which is the top layer where various network applications such as load balancer, firewalls, and network engineering tools are developed. These applications are designed to achieve specific network objectives and interact with the SDN controller via well-defined API. The middle layer hosts the SDN controllers, which manage the network control logic. The controller serves as a centralized entity responsible for decision making and policy enforcement across entire network. The bottom layer consists of SDN-enabled network devices such as routers, switches, firewalls, and the packet inspection units. These devices execute the forwarding decisions and data plane functions as instructed by the controller. Now there are some APIs you defined in the SDN architecture. First one is the northbound API. They, these APIs allow communication between the application layer and SDN controller. Applications use northbound APIs to retrieve network information and issue control commands. For example, a load balancing application may define specific rules that are transmitted to the controller via northbound APIs. These APIs are abstract. These APIs abstract the underlying network complexity from the application developed. Then there is a southbound APIs. These enable the SDN controller to communicate with the data plane services. Through southbound APIs, the controller configures the forwarding behavior, access control policies, QoS settings, and on switches and routers. OpenFlow is the most widely used southbound API. And there is a controller to controller APIs, which is also known as East-West APIs. These APIs allow communication between controllers within the same or across different administrative domains. They are crucial for ensuring redundancy and fault tolerance. For example, if one controller fails, another can seamlessly take over, maintaining network stability. Controller-to-controller communications also enable sharing of topology or application data between domains, facilitating end-to-end network services across different SDN environments. Now let's talk about the three main pillars of the SDN. The SDN architecture is built upon three foundational principles. The first is the separation of control and data planes. Traditional networks tightly couple control plane and data planes within the same device, as we have discussed in the previous slides. SDN decouples them, placing control logic in a centralized controller, while the data plane remains distributed across the network. This separation simplifies network device design and improves the network flexibility. The second pillar is centralized network control. SDN controller acts as the brain of the network. It maintains a global view of the network and optimizes routing and policy decisions across multiple devices. Examples of SDN controllers include Open Daylight, ONAS, RYU, and Floodlight. Last and third third pillar is network programmability via API. Accordingly, SDN enables dynamic software-based control over network behavior through APIs. Applications can program the network using northbound APIs, while the controller uses the southbound APIs to apply those instructions to the network devices. Now let's discuss the differences between the control plane and data plane. From functional perspective, control plane is responsible for making routing and forwarding decisions. It determines how traffic should flow through the network. In SDN, this logic is centralized in the controller, whereas the data plane is responsible for forwarding packets based on instructions from the control plane. It performs actions like packet switching, header matching, access control, and queue management. In traditional networks, both planes reside within each networking device, as we have discussed before. In SDN, the control plane is centralized, while the data plane remains distributed. Now let's have a look on southbound APIs in detail. Southbound APIs allow the SDN controller to manage the behavior of the data plane devices. These APIs define flow entries, for example, match action rules, and specify packet handling actions such as forward, drop, or modify, and collect network statistics. Commonly used southbound APIs are OpenFlow, which is the most widely adopted southbound protocol. It supports flow table programming, traffic forwarding, and statistics collection. There is another common API available that is used with Open vSwitch for configuring interfaces, QoS settings, tunnels, and bridges. Yet another commonly used API is the P4 runtime, which allows programming of matching action tables in P4 enabled devices for custom data planes. Netconfig slash Yang is another device configuration through netconfig or Yang is also used for device configurations through structured data model. There are some SNMP M4CS APIs that are also used in limited and legacy scenarios. Among these, OpenFlow or OVSDB are the most commonly used in both experimental and production environments. Now let's have a look at the northbound APIs. Northbound APIs allow applications to interact with controller for purposes such as policy enforcement, analytics, traffic engineering, and network monitoring. Popular northbound APIs are shown on this slide. Among these one, RESTful APIs are most widely used and familiar to many developers. gRPC, GraphQL APIs are also lightweight and efficient options for real-time communications. And there are some language-specific APIs, for example, Java and Python APIs for direct application development. There are intent-based APIs also available that allows developers to specify high-level network intents without implementation logic. Netconfig or Yang is also useful for configuration of data exchange. You can also use the CLI interfaces or the GUI interfaces that provide manual configuration and visualization tools. RESTful APIs remain the most commonly used due to their simplicity and broader adoption in the application development. From the applications point of view, the application layer in SDN consists of software modules that use northbound APIs to define high-level network behavior and policies. These applications can be tailored by network operators to meet specific needs. Examples of SDN applications are load balancers, firewalls, are the intrusion detection systems, bandwidth management, policy-based routing, traffic engineering applications. These applications enable flexible programming and efficient management of network devices. So the control layer, it is the core of the SDN architecture. It is logically centralized. Sorry. The control layer is core of the SDN architecture. It is logically centralized software platform that maintains a global view of the network, translates high-level application policies into low-level commands, interfaces with both applications and network devices, and it supports multiple concurrent applications. Controller also communicate with peer controllers to ensure redundancy, resilience across multiple networks domains. So let's have a look at the different commonly used SDN controllers. SDN controllers differ in their architecture, supported protocols, and programming environments. The choice of controller depends on the network requirements, supported features, and developer preferences. The commonly used SDN controllers are the OpenDaylight, as we have discussed before. It is Java-based modular open source controller that supports OpenFlow, NetConfig, and BGP APIs. It is suitable for enterprise and telecom networks. Frontlight is also another SDN controller which is Java based with REST API support. It offers compatibility with OpenFlow version 1 and version 1.3 and is often used in enterprise environments. RYU is a Python-based controller with simple structure suitable for rapid prototyping and academic research. ONAS stands for Open Networking Operating System. It is a Java-based platform designed for scalability and high availability in carrier grid networks. There are some proprietary controllers also available, such as Cisco Epic IM, which is intent-based controller tailored for Cisco environments. POX is another Python-based lightweight controller. It is often used in academic settings. As we have discussed, P4 controllers are also available. These are used for P4 capable devices for customized packet processing. Each controller has core features in common, but they may differ in extensibility, supported APIs, and integration capabilities. Selecting the right controller requires careful evaluation of project needs and development environment. Now let's talk about the different controller to controller APIs that are used for communications between the controller to controller, and they are also used as east-west APIs. In software-defined networking, controller-to-controller communication is essential in distributed SDN architectures. These architectures involve multiple controllers working together to provide fault tolerance, high availability, scalability, and geographic distribution. While there is no universally adopted standard for C2C communications, several frameworks and protocols and approaches are used in practice. We have shown we have shown different kinds of APIs which can be used for controller to controller applications, controller to controller communications. For example, RESTful APIs are custom APIs often supported by controllers like RYU, ONAS, and Open Daylight. These APIs are not standardized but allow basic state sharing and interaction. gRPC is another C2C API, which is a messaging framework used for efficient intercontroller communications. It is supported by ONAS. It is not standardized but provides high performance message exchange. SDNI, which stands for SDN interface, it is a conceptual protocol with some existing prototypes. It supports inter-domain flow state sharing, which is critical for trust-based information exchange and global optimization. However, it is not widely adopted. There is also a another controller-to-controller API available, which is BGP-LS. It is also the full form is border gateway protocol link state API. A standardized protocol often used in as it is a standardized protocol often used in WAN SDN scenarios. It allows topology and state sharing between controllers and different administrative domains. There is also possibility to use the internal messaging bus, which is used in clustered deployments such as Open Daylight. This method enables inter-cluster messaging and coordination. It is not standardized but helps in making global optimal decisions within the controller structure controller cluster. After talking the east to west or controller to controller APIs, let's have a look at the infrastructure layer. The infrastructure layer is also known as the data plane layer. Consists of devices responsible for actual packet forwarding. These include switches, routers, firewalls, specialized programmable hardware. These devices implement forwarding rules received from controller and can also collect statistics and send event notifications. Key SDN compatible infrastructure devices are shown on this slide, and among these one, OpenVSwitch is a popular open source software which is used in Linux environments. It supports OpenFlow, OVSDB, and NetConfig APIs. There is many-net hosts also available, which are emulated network devices used primarily in SDN testing and research. They support the OpenFlow. There are some hardware switches include like Pika-8, Big Switch, Novi Switch, Dell EMC, HP Flex Fabric, Barefoot, Tofino, and Whitebox switches. Many of these devices support OpenFlow and some support P4 runtime also. Selection of the infrastructure devices should align with the controller and network goals, ensuring API's compatibility and feature support.
So let's now summarize our discussion on the SDN concepts and definitions. We can see that software-defined network architecture is quite powerful because it centralizes the control plane, so the centralized decisions can be made. This provides flexibility and also reduce the computational costs. In addition to this one, there is a rapid innovation is possible because new software applications can be developed that can improve the security, quality of service, and the control the data plane configurations.
For the key components of software-defined networking architecture. SDN is built on layered architecture that promotes centralization, programmability, and flexibility. The three fundamental layers of SDN architecture are application layer, control layer, and infrastructure layer. The application layer contains network applications that define desired behavior and policies, whereas the control layer hosts the SDN controller, which translates the application policies into device instructions. And the infrastructure layer comprises of the data plane devices, for example, switches and routers, which is basically a programmable hardware that executes the forwarding decisions. Basically, the key components of SDN networks are SDN applications, which provides the custom functionality for the users, and the SDN controllers, which basically centralizes the control plane and decision making, and then the data plane devices, which are the forwarding devices. We have talked about the SDN applications in the previous slides. Let's talk about the SDN applications in details. SDN applications interact with controllers to enforce policies and implement network logic. Common examples of the SDN applications are the load balancing applications, access control or firewall applications, intrusion detection systems or IDS, traffic engineering applications, quality of service managers, deep packet inspection, and security monitoring. These applications relies on the statistics collected by the controller from the data plane devices, and then makes these suitable decisions according to the given rules or some intelligent models. In fact, these applications leverages the controller's global network view and northbound APIs to enforce dynamic fine-grained policies across the network. As an example, the traffic engineering application may be used to detect congestion and dynamically reroute the traffic flows. Now for the SDN controller, which is basically the part of the control plane of the SDN architecture, it acts as a network central intelligence device. It maintains a global network view and programs forwarding rules to data plane devices. The key features of a SDN controller are that it is generally logically centralized, and it is also physically distributed, and it has several interfaces like the northbound APIs, southbound APIs, and east to west APIs, which are used for controller to controller communications. The common SDN controllers that are available in the market are the Open Daylight, ONAS, RYU, and Floodlight. The typical use of a controller in a data center is that it can be used to redirect traffic to avoid congestion based on real-time statistics collected from the infrastructure. Not only based on the statistics, but some intelligent machine learning or AI models can be used to determine the alternate paths or the optimal alternate paths. Now for the northbound APIs, which are the application interface in the SDN architecture, these enable applications to communicate with SDN controller. The main functions of the northbound APIs are to define network policies, perform networking and analytics, perform monitoring and analytics, support intent-based networking. And the commonly used northbound APIs, as we have seen in the previous slides, are the RESTful APIs, gRPC, GraphQL. The typical use of northbound APIs as a firewall application that might use a northbound APIs to block malicious traffic from a specific IP addresses. Now for the southbound APIs, which are generally called as a device communication interface, these allow the controller to manage infrastructure devices. The primary protocols that are used for southbound APIs are the OpenFlow, which is most widely adopted SDN protocol. It defines how the controller programs switches using flow tables. Other some examples of the southbound APIs are the netconfig, OVSDB, gRPC, P4 runtime, and these are the additional options that can be used depending on the device capabilities. The controller generally sends an OpenFlow command to switch to drop packets from a suspicious IP address. This is a typical example where southbound APIs are used. From the forwarding devices, which is the part of the data plane, these implements the flow rules from the controller, and these are generally the switching or the routing hardware. The key characteristics of the forwarding devices should be that it should be simplified to design, no embedded control logic should exist here, and it should rely on flow tables for forwarding decisions. In fact, it should be able to interact with the controller when encountering unknown flows. Examples of the forwarding devices are the Open vSwitch that is used with the Linux-based operating systems and P4-enabled switches. To summarize the SDN architecture, it has three layers: application layer, control layer, and infrastructure layer. Application layer hosts network applications defining policies and desired behavior, whereas the control layer consists of SDN controllers that translate policies into flow rules and maintain global network state. Infrastructure layer includes physical and virtual devices such as routers, and switches that enforce flow rules. The SDN layers communicate via northbound and southbound APIs that enables the programmability, abstraction, and centralized controls. Now, after having looking at the key components of the SDN architecture, let's understand how the SDN has evolved in the recent era. It will help contextualizing the capabilities of SDN and for its future potential for the future generations of networks as a 6G and 7G networks. The journey of the software-defined networks can be divided into basically six stages. The first stage was the pre-SDN era that elapses from 1980s to 2000. It was dominated by traditional networking with static hardware-defined infrastructure. The second era it elapses from 1990s to 2007, which is basically an early which has early experiments with network programmability by different researchers groups from the academia and industry. The third stage was the SDN introduction that elapses from 2008 to 2011. The SDN concepts formally emerged, and OpenFlow and work at Stanford brought the SDN into spotlight. The fourth stage is the commercialization and ecosystem growth that was during the 2011 to 2015. This era was seen a widespread adoption of commercial products and community engagement. And there was a research beyond the OpenFlow because the early research was mainly focused on the OpenFlow. During 2015 to 2019, generalized SDN concepts with new APIs were introduced. They increased the flexibility and broader application domains. And finally, in the current era, which is the modern SDN, the integration with AI and ML algorithms, internet-based networking, and machine learning to optimize decision-making and automated operations are the main research fields in this era. Modern SDN architecture benefits greatly from its centralized architecture, making it an ideal platform for AI-driven enhancements in network automation, security, and performance applications.
In the pre-SDN era, where mostly there was traditional networks, that means from 1980s to 2000, the major things was that there was distributed control plane devices where each router and switch had embedded control logic, for example, OSPF switching and BGP protocols, etc. And furthermore, the configurations of the devices and provisioning was static, and it was generally through static CLI based tools. And there was an issue also, the vendor lock-in. I mean, the enterprises were locked with some particular vendor. What they have deployed before. And the experimentation and innovation with the networking in the networking domain was quite slow, and it was impossible for the network operators or the enterprise network organizations to conduct the experimentation and research. So that's why this was the basically the issues that were existing in the traditional network era. And the significance was in this era was that MPLS or IPv6 was also introduced, and for this purpose, all the devices were required to upgrade their firmwares and different softwares to support these new protocols. Now, in the early programmable era, which was which elapsed from 1990s to 2007, there were active networks, basically that packets carried executable code that was quite complex and insecure. And also there was some realization of the control plane separation. The notable efforts were the 4CES, that was the initiative by the IETF, and they produced a framework for controller and forwarding element separation. And also there was RCP was introduced, that was a centralization of the routing logic. The significant development in this area was that these ideas that we have discussed before laid the groundwork, but lacked real-world deployment due to complexity and lack of vendor support. Then, in the emergence of STM era, which was 2008 to 2011, OpenFlow was proposed by Stanford in 2008, and this was a standardized protocol to control the forwarding plane switches. It also enabled the researchers to program the networking in vendor-agnostic way. And key developments in this era was basically the Ethan project, that was an early controller-based security framework, and also the Knox controller, which was the first OpenFlow controller it was introduced. And Jenny and Planet Lab also provided the experimental platform for SDN testing. The significance of this era is that OpenFlow made the SDN practical and accessible to various researchers in academia and in industry. And from 2011 to 2015, it was the commercialization and ecosystem growth for SDN networks. In this period, ONF, which is the Open Networking Foundation, it was founded in 2011 to promote SDN and OpenFlow. Major vendors like Google, Facebook, Cisco, VMware, they also joined the SDN movement, and also started conducting research in this architecture. And some new controllers like OpenDaylight, ONAS, and Floodlight controllers were also introduced. In this era, there was real-time applications of the SDN. For example, Google V4VN that used the SDN for inter-data center traffic engineering. And also VMware NSX also supported the network virtualization platform that was built on the software-defined networks. Basically, in this era, SDN became more than a research idea. It was now an industry trend. Then in 2015 to 2019, this was the beyond OpenFlow era, basically because in the previous era, the most of the research was focused on the OpenFlow. And the issues with the OpenFlow was that it was not flexible or expressive enough for all use cases. And it also has the poor support for packet processing and stateful functions. The new developments in this era was the P4 language, which was protocol independent packet processors. This language defined the packet forwarding behavior to fine-grained level. Furthermore, the rise of SDN plus network function virtualization used to orchestrate and manage virtual network functions like firewalls, load balancers. And in this era, basically the cloud providers, edge providers, and telecom providers, they started to use the SDN within their products. Finally, in the current era, modern SDN, the internet-based networking and AI-driven networking has been focused. In IBM, users define what they want. The system figures out how to do it, and with the AML, with the machine learning or artificial intelligence, SDN controllers can use intelligent algorithms or models to predict the traffic and detect the anomalies and perform some optimization. And there was a cloud native SDN. Some works are also in progress that integrates directly with the Kubernetes containers and microservices. And there is also concept of disaggregated networks. That's open hardware like the white box, which is controlled by open software, open source softwares. The important thing in the current era is that telecom operators are using ONAS plus P4 for programmable 5G network slices. Actually, this will be also based on the 6G networks is also based on the SDN that relies on the centralization and distributed control, and the SDN capabilities like automation, orchestration, characteristics. So that's all what we have discussed today in this session. In the next upcoming sessions, we shall talk about the OpenFlow and P4 languages, and we'll also see how can we configure and how can we use and do experiments with the existing protocols and the new protocol and new protocols. Thank you very much.